Hello everyone, and welcome to this video where I'll be taking you through a sample question related to the objective called Determine the second derivative of a parametrically defined curve with polynomial and radical functions. So I'm going to be on Knewton.com in their Knewton Alta program. I'm in the instructor mode, so you'll be able to see the answer here coming up, and I'll of course show you how they went about getting this on paper. And if you're somewhat familiar with the material, you've done some reading or some studying up already, I would suggest you pause the video, try to work out the question yourself first, and then come back and watch me do it and see how your work compares to mine and see how well you're grasping the material. Okay, so here we are asked to determine the second derivative of the parametrically defined curve represented by the equations x of t equals negative 6t squared minus 3t minus 5 and y of t equals negative 6t cubed minus 8t squared minus 2t plus 2, right? So a couple polynomial equations. And the radical, and this example is very similar to ones with the radical functions that were mentioned in the title. So if you can do this one, you should probably be able to do the others with radicals. Okay, so again, the parametric equations, the x and y coordinate of some point on the xy plane depend on this parameter t. And as you change the value of t, you'll trace out more and more points, more and more xy coordinates, and trace out some curve. Now, in previous videos on another objective from this same assignment, we were asked to find the first derivative, which was slopes of tangents to the curve being traced out, right? Which direction was the curve going in at a particular moment? So here we're asked to find the second derivative. All right, so you may recall from maybe a previous calculus, Calc 1, recall that this, d with the square here, y over dx with the square there, this was applying the differentiation operation twice to this y, which is a function of x. So you could refer to this as y double prime of x or just y double prime. This told us about the concavity of the original curve, right? Y equals some function of x. And wherever y double prime was positive, f, right, the original function was concave up, right? So curving upward like this, curling upward. And wherever the second derivative was negative, right, less than 0, the graph of the original function, which I'm calling f here, would be concave down. So curling downward like that. And wherever it was equal to 0, if the concavity were changing from down to up or up to down at that point, then you'd have an inflection point. But this second derivative help us determine the concavity of a curve, which way a curve was turning, upward or downward. All right, so here in this problem, the equations for our curve, the parametric equations, we have x of t is negative 6t squared minus 3t minus 5. And y of t, the y coordinate, depends on t the following way: negative 6t cubed minus 8t squared minus 2t plus 2. There. So to get to the second derivative, you need to find the first derivative initially, right? So let's go for the first derivative. And hopefully you recall. If you don't, I'll write it again here, how to find the first derivative really quickly when your x and y coordinate depend on some parameter, which in this case is t. First derivative, dy over dx, which, was slopes of tangent lines to the curve. Or you could call it y prime of x, right, depending on x. This is equivalent to, dy over dt. So the derivative of y with respect to t. So I'm going to point this out. Notice that when we're doing first derivative parametrically, this d over dx operator, the differential operator, is being applied to y, and that's what's going on up here in the numerator. All right. So dy over dt divided by, and then dx over dt, which we could call, y prime of t divided by x prime, depending on t. And we have these. We can easily find these. The derivative of y with respect to t, this is a simple polynomial. Let's go term by term here with the power rule. All right, so the numerator with y prime dy over dt would be negative 18t squared minus 16t to the first minus 2, and the denominator is the derivative of x, the x function with respect to t, this polynomial. Again, simple term by term, apply the power rule. So negative 12t, then minus 3. And that's this expression here is the first derivative. Now you could try some factoring. I mean, this numerator you could factor out a negative 2, the denominator you could factor out a negative 3, but yeah, I really don't see, though, any way to factor and simplify this fraction any further. So I'm just going to leave this the way it is. All right, so now we have an expression for the first derivative, right? So if I know the value of t at a particular point, I could tell you the slope of the tangent line at that point. So now we're going to move into, I guess I don't know why I wrote the arrow. I'm just going to put up another piece of paper here. I'm going to move to finding the second derivative, which will help us determine, derivative. And that notation was this, it's d squared. So it's, the d over dx twice applied to y. So again, I'll write that like that. It's the derivative, with respect to x, and the derivative with respect to x applied to y, like that. So like from the inside out here, you apply the derivative to y and then apply the derivative again to that. It's the instantaneous rate of change with respect to x. All right, well this here, in this notation, that's dy over dx. I could just call that y prime, or y prime of x, like I have here. So I could call this, the derivative of the first derivative with respect to x. And of course, hopefully that makes sense. The derivative of the first derivative with respect to x will give me the second derivative with respect to x, right? Derivative of the derivative. And since things are defined parametrically, I'm going to just reapply, or now this is a first derivative, right? Again, the second derivative of y is the first derivative of y prime. And we know how to find the first derivative of stuff. You take the derivative of that thing, right? So the derivative of y prime with respect to t in the numerator, then divided by, and then once again, I'm just using this form here, the derivative of x, the derivative of the independent variable x with respect to t in the denominator. And then we'll simplify this after filling this in. All right, so now y prime though. Remember y prime in terms of x, or sorry, y prime, let's say in terms of t that we got earlier, right? This was y prime, this line up here, the first derivative. Was this, again, negative 18t squared minus 16t minus 2 divided by negative 12t minus 3. It is a quotient, right? A fraction. So I'm going to, when I find the numerator of my second derivative expression here, this dy prime over dt, I'm going to be applying the quotient rule to this. All right, so it's a little bit hairy here. Now, hopefully you apply the quotient rule. All right, so the derivative of y prime with respect to t, it's a big thing for the quotient rule here. All right, it's the denominator, so negative 12t minus 3 multiplied by the derivative of the numerator. And that would be negative 36t minus 16. Right, so the denominator, the way it is, times the derivative of the numerator, and minus the numerator the way it is. So negative 18t squared minus 16t minus 2 multiplied by the derivative of the denominator, which is simply negative 12. Our clutter tightness over here. And then all of that divided by the denominator, so negative 12t minus 3 squared. Right. So low d high minus high d low over low low. However you want to remember that quotient rule. All right, now I'm noticing expanding on this, multiplying this out. All right, so I've got a calculator up off on my side here. You can't see it, so I'm just gonna be multiplying things, numbers with the calculator. So when we expand this stuff out, here I'm foiling, distribute the negative 12t, distribute the negative 3, combine like terms. Let's see, 12 times 36 is negative 12 times negative 36. So that'd be a negative 12t times negative 36 would be positive 432t squared. And then I'll just keep the t terms. We'll put all this stuff together after this. Then 12 times 16, 192. So they got plus 192t. So that's the negative 12t distributed. Then 3 times 36, 90 and 18. So 108 plus 108t. and then plus 48, negative 3 times negative 16. All right, and then here, I'm going to take negative 12. We have the opposite of negative 12, so I'm going to be putting positive 12 times all this. Okay, so now 12 times 18, well, negative 18 could be half of 12 times 36. So that's 216. That's a minus 216 t squared. And we already saw 12 times 16 earlier, right? That's 192. So minus 192t. And then 12 times negative 2 in there, minus 24. All right, we'll simplify some terms. And then down here, you got, negative 12t minus 3 squared, be 144t squared. And, plus 36 plus another 36, so plus 72t, and then plus 9. All right, so sorry about the algebra here. You probably hopefully already skipped through this. I might pause it for the next one when we do some algebra. So you know what, I'm just going to combine like terms right now and write the final result. So I'm pausing it, come right back. Okay, so I did the algebra, combined some like terms here. I multiplied the top and bottom by a third, since all these have a common factor of 3, all these coefficients. So we end up with the derivative of y prime with respect to t is 72t squared plus 36t plus 8, all divided by 48t squared plus 24t plus 3. All right, so keep this in mind. I'll box this in. This is not the answer yet. All right, this is our first derivative in terms of t, taking the derivative of that. And this expression then is going to go up here in this numerator. As again, one more time, the second derivative with respect to x is the first derivative with respect to x of the derivative, right? The derivative of the derivative. So we just took the derivative of our first derivative in terms of t, and then this gets divided by the derivative of x with respect to t, which we already have from earlier. And the derivative of x with respect to t is negative 12t minus 3. So that denominator doesn't change, it's the numerator for this second derivative. All right, so our second derivative of y with respect to x is this dy prime over dt, this thing here. So I'll put it in parentheses, 72t squared plus 36t plus 8 divided by, and then 48t squared plus 24t plus 3. That's the dy prime over dt. And divided by, all that divided by, and then dx over dt, which is simply, as we stated earlier, right, negative 12t minus 3, right, the derivative of that. All right, now this is great. All right, I mean, if I were testing you, this would be acceptable to me, although it's not completely simplified, right? So take this here, this is technically over 1. I'm going to rewrite it so it's not a complex fraction. So I'll be doing is taking this fraction in the numerator and multiplying by the reciprocal of the fraction in the denominator. So the denominator is the following, right? So the second derivative of y with respect to x is 72t squared plus 36t plus 8 in the numerator. And the denominator will be the product of 48t squared plus 24t plus 3 and negative 12t minus 3. And if you were to multiply these out, you'd have to I'd distribute the negative 12t to these three terms and then distribute the -3 to these three terms, and then combine like terms. And I already did that off to the side. I don't want to bore you with any more algebra than is already in here. But if you distribute this, combine like terms, you'll end up with 576t cubed plus 432t squared plus 108t plus 9. And that doesn't really have any factor common to this numerator, so the numerator is the way it is, 72t squared plus 36t plus 8. There you go. All right, this expression here is what they're asking for. I know that was quite a lot of algebra there, and the only reason there was so much is because of the degrees of the polynomials, but this is it. This expression in terms of t will tell you the concavity of the curve at any moment. You just need to know the value of t, the value of the parameter at that point. Right, and once you plug it in here, if it's positive, it'll be on part of a curve that's concave, concave up. If you plug in a value of t and you're at a specific moment and this ends up being negative, you'll be at a point where you're concave down. And if this ends up being 0, or undefined, it may be at a point of inflection, but that's not guaranteed. All right, so going back to the site just to double check, right, if you look through all this, the algebra I did was basically all this here. But if you look at that's in the explanation, you look at the correct answer. I didn't put the negative out. My apologies. Yeah, this 576 plus 432 plus 108 plus 9, right? They factored the negative out. I meant to do that, right? Because look how, both in this factor here, they're both, negative, -12, -3. So I can pull the negative out, make these plus, and then negative comes out front. So this should have a negative, right? So my apologies for that. Hopefully that didn't throw you off too much, but yes, that's a lot of algebra. So it's the opposite of this. Still, this expression here, as was given here, gives us the concavity to the curve represented by these parametric equations. All right. So again, a little annoying with the algebra, but the key, right, and this will come up in other videos, the key is this right here. Or if you want the second derivative with respect to x, just think of that as the first derivative of the first derivative. All right, it's the derivative of the derivative. And then this first derivative, you found earlier, right? You found the first derivative earlier. So then applying that parametric rule to it, you're taking the derivative of y prime with respect to t divided by, and then the derivative of x with respect to t, right? Applying the same principle that you do for the first derivative to this second derivative. All right, so again, if that's not clear, hopefully coming videos where I'm going to be doing this again with just different kinds of functions will help out. All right, and thank you very much for watching.